Okay. So titration is a way of determining an unknown concentration. So it's a lab technique. Probably one of the most common lab techniques, because we have lots of things that are in our solutions. We want to find out how concentrated they are. We need to react those solutions. Okay, so when you add the same number of moles of acid and base, the solution is neutral. That's because H plus OH minus makes water. So if my acid adds the H plus, if my base adds the OH minus, if I add them equally, I don't have any of those left over, and I've got a neutral solution. So by measuring the amount of base you add, you can determine the concentration of the acid, as long as you know the concentration of the base. So the idea behind a titration is you take a known concentration and react it with an unknown concentration to find that unknown concentration. React what you know with something you don't know, so you use the one you know to figure out the one you don't know. Yeah, so if you can do it the other way too. As long as you know one of them, you can use it to find the other. Fact is, so tomorrow you're going to determine an unknown base. Well, actually, no, you're going to determine an unknown acid, its concentration. So this is a titration. Take a known concentration to find the unknown concentration. And you have to have a way of knowing when you've made that switch. Okay? So for acid bases, I've got some acid here. This is a little bit of hydrochloric acid. And I've got some base. This is a little bit of sodium hydroxide. Okay. So acid, base. And to tell the difference between the two, we have something called an indicator. The one we're using is phenolphthalein. It's my favorite word because it's got the second pH is silent. Okay, phenolphthalein. Okay, and in acid, phenolphthalein is clear. But in base, phenolphthalein is pink. So you will know when you have too much base. Here I know I have acid left over because it's staying clear. So what you do is you add the base until it turns pink. Just the first drop of pink is what you want to see. Make sense? So it's clear in acid, pink in base. So you add the base until it turns pink. So that's how they know they're equal to each other. Okay? Pretty easy technique to talk about. A little harder to carry out. We'll see that in a second. So it takes 45 milliliters of a 1 molar sodium hydroxide solution to neutralize 57 milliliters of HCl. What is the concentration of the HCl? Okay, so I have a volume and a molarity of base, so I can figure out the moles of base. Right? And then I can go from the moles of base to the moles of acid using the balanced equation. And then once I get moles of acid, then I'll have moles in milliliters of acid. So I'll be able to get the molarity.
Since they're both the same amount of moles, can we use the other formula? Because isn't it the same concentration, just a different volume?
No, we don't know what the molar concentration is. Okay, so that's what we're trying to find. Okay. And it can't be the same molar concentration because the equal volumes, if they were equal molar, equal volumes would have reacted. Okay. So let's start off with what our plan was. 1.0 molar times 0.045 liters is 0.045 moles of NaOH. Everybody okay with where I got 0.045 from? Okay. And then I write my equation, HCl plus NaOH makes water, HOH, and NaCl. Na is 1 plus, Cl is 1 minus, that's the right equation. So now I can say my 0.045 moles of NaOH I want to get rid of moles of NaOH. Turn it to moles of acid, HCl. That's 1 and 1. So that's 0.045 moles. Have that divided by 0.0457 liters, because that's how much of that acid I used. And I get that it is 0.79 molar. And that makes sense because it was a 1 mole to 1 mole ratio. It took more of the HCl, so the HCl had to be less concentrated. So let's look what it looks like when you're doing a lab. Okay? So this piece of equipment, so you have the clamps, we've used these before. These things, these long tubes with valves on the bottom, are called burettes. Okay? Depends on who you talk to, which way they spell it. It's either burette or burette. Depends on who you talk to. I'm lazy, I write that one. Okay, so what it is just a long tube measured in milliliters with 0 at the bottom and 50 at the top. And I got it wrong, 50 at the top, 0 at the bottom. No, 0 at the top, 50 on the bottom. Okay, so what you do with these is you can measure how much comes out. You can open up the valve and let it come out. So to do a titration, I need to measure both of my solutions. So to measure the solutions, here's the technique. Okay, first of all, this is going to be, actually, I want to do this. I want to do oxalic acid, H2C2O4. Okay, and we want to find the concentration, use that to find the concentration of an OH minus sodium hydroxide solution. Okay, so I need to fill one of these with the oxalic acid. Okay, but if there's any drops in here, I don't want them to be anything but oxalic acid. So the technique is to pour in just a couple of milliliters, roll it around inside so you wet the whole inside, then dump that out. Let it go through the tip, and you can actually pour the extra out the top. And you do that 2 more times. So you rinse it 3 times. By the 3rd time, you're sure that every drop in there is the oxalic acid we want to use. Make sense? And in the interest of time, I'm only going to do it twice. And then I fill it all the way. Okay. Fill it all the way. I'm using up all my stuff, so. Okay. And then you have to fill up the tip Otherwise, you're not measuring how much comes out. Makes sense. You've got to have that tip filled. Okay, because 0 is not at the bottom. There's a gap. So what you do is you measure where you start and where you end. So for my oxalic acid, I'm starting at 24.6 milliliters. So on my acid, I start off at 24.6 milliliters. Okay, and my base, I've got some sodium hydroxide here. And I'm going to use the same technique. So I rinse it 3 times and then fill it up. Okay, once again, in the interest of time, I'm not going to take the time to do it all, but understand why you would want to do that, right? Just like the cuvettes, it makes sense that if you had to rinse the drops out of the cuvettes, you've been watering down your drops along the way. Same thing happened in here. Okay, so I'll fill that up, and I need a starting concentration, a starting volume for it too. After I fill up the tip. Okay, fill up the tip. A little tricky sometimes, it gets a little air bubble in there. And this is starting at 7.4 milliliters. Because remember, 0's at the top. So the base was 7.4 milliliters. Okay? So then I take a flask, and I didn't bring enough flasks out. Gotta go grab one. I happen to know where there are some. Take a flask. And I'm going to take out some of the acid. I want it to be about 10 milliliters so I get another sig fig. Makes sense? If I stop at 8, then I lose a sig fig. So I was at 26.4, right? So 24.6, so I just got to get someplace past 34. Okay, now that was my acid. And if I put a drop of phenolphthalein in there, it stays clear. It only takes 1 drop. Okay, and then I add the base until it turns pink and stays pink. Come on. I know the numbers. I'm going to slow down when you get there so you get just 1 or 2 drops at a time. You don't want to go fast because it starts hanging around a little longer. So right now I know that there's more base than acid. You want to get so 1 drop makes a difference. So I'm going to put 1 drop of acid. 1 drop of acid should clear it up if I've done my job. So we're pretty sure we're right at the point where the acid and the base are equal to each other, because 1 drop changes it back and forth. So now I need my final numbers. So my acid ended up at 35.9. And my base ended up at 35.3. So that means that I used my acid, I used 24.6 to 35.9. That is 10.3 of acid. And base I used 7.4 from 35.3 is 7 would be 28. So 27.9. 27.9 milliliters of base. And I know that the base, I know the base was 1.0 molar. Yeah. So my acid was oxalic acid, which is H2C2O4, oxalate. It's a polyatomic ion we haven't used very much, but it's on the list. Okay. And to that I added sodium hydroxide. So my equation is going to be Na next to C2O4 and H next to OH. Na is 1 plus, and C2O4, I can tell because it took two H's that C2O4 was 2 minus. So it's got to be Na2CO4, so C2O4. And that means I'm going to need 2 NaOHs, and I'll make 2 waters. Nothing starting here. We're just seeing where we get the numbers from that we do this. Okay? So then I can do 0.0279 liters times 1.0 molar gives me 0.0279 moles of NaOH. My 0.0279 moles of NaOH. I can get rid of moles of NaOH. Change it to moles of HCl or H2C2O4, and that is 1 and 2 out of my balanced equation. So 27.0279 divided by 2 is 0.0140 moles. And I divide that by the 0.0103 liters of my acid. Yeah. 0.0, that's 279 divided by 2. It's going to be 13.5. That's a 27. Oh, it's 11.3? Okay, I did that. I did it in my head. I'll fix that. Okay, so that means we do this. Okay, and I just push divided by 11.3. And that will get me 1.23 molar. That's bizarre. I didn't know. It's unknown. I didn't know what the concentration was. Now we believe it's 1.23 molar. So that's how we get the numbers. Tomorrow you're going to do that with vinegar and sodium hydroxide. Okay? And there's going to be enough that where you stop with one, you can start the next one. Because I still got acid left in that container, and it's more than 10 milliliters. I can do another experiment with that acid. And I just start at 35.9 milliliters, let out 10 more, past the 45.9, go back and forth. I'd have to fill up my sodium hydroxide because it took 27, and I'm well past that. I only got 10 left. Yeah. Yeah, I knew the one. So I knew it was 1.0 molar. That's the only reason I can do this. I used the base I knew to find the acid I didn't know. Man, that's a lot of work. Don't you wish there was a shorter way to do this? Okay, we don't need to do a net ionic equation again. But what is the net ionic equation every time you do an acid base? H plus OH minus makes H2O. Every time, right? That is always the net ionic equation. So if that's always the net ionic equation, then at the equivalence point, the moles of H plus have to equal the moles of OH minus. That's pretty obvious, right? If they don't, then you have too much. You either have too much acid or too much base. Okay. So with that in mind, we can shorten this down. This shows up in no book I've ever seen. Okay. But if you take the molarity of the acid times the volume of the acid times the number of H's in the acid, that's going to equal the molarity of the base times the volume of the base times the number of OH minuses in the base. Because molarity times liter will tell me moles of acid, and the number of H's in that acid, if I multiply by that, that'll tell me how many moles of H I have. Molarity times liters will give me moles of OH minus. Right? And then if I multiply it by the number of OH minuses, that'll tell me how many moles of OH minus I have. This is really just moles of H plus equals moles of H minus. And it's going to involve us doing all the math we did for that last example. All the numbers we used are all going to show up in that equation, except for we don't have to change them to liters. Because I'd be 1,000 on this side and 1,000 on that side. Right? So it'd be the same on either side. So this will work in milliliters. So let's see how it changes our problems. Take 67 milliliters of 0.5 molar sulfuric acid to neutralize 15 milliliters of aluminum hydroxide. What was the concentration of the aluminum hydroxide? Well, we could do molarity times liters, find moles of H2SO4, write a balanced equation to figure out how many moles of AlOH3, then take and divide by the volume of the AlOH3. I could do all those steps again. I'd get the answer. Or I can do Ma times Va times H's equals Mb times Vb times number of OH's. Okay. Do I have those numbers? I know the molarity of the acid was 67. I know the volume, it was 0.7. I know the volume was 67 milliliters, and it's H2SO4, so it's got two H's. I know the volume of the base. I know it's AlOH3, so it's got three OH's. So I have enough information to find the molarity of the base. All I have to do is divide both sides by the volume of the base and the number of OH's. So my molarity of the base is going to be the molarity of the acid, 0.500 molar, times its volume, 0.67 milliliters, times the number of H's, 2. Divided by the volume of the base, 15 milliliters, times the number of OH minuses, 3. The 2 and the 3 are counted numbers, so they have unlimited sig figs. So 0.5 times 67 times 2 divided by 15 divided by 3 equals 1.5. I only have 2 sig figs in my 67 and my 15. 5 molar, because that's the only unit I have left. See how that was a lot faster? It has all the pieces. I would get that 2, 3 from my moles of H plus and moles my moles of H2SO4 to moles of AlOH3 out of my balanced equation. Those would be the coefficients. So these are the coefficients you get out of the equation. This is moles times the coefficient divided by liters. All the math you would do along the way is there. It only works because H plus equals OH minus. So you go ahead and do this one and see if we come up with the same answer. While I do dishes. Well, actually, I got to remember which one's the acid. So I'll do it later. Oh, the acid. Ooh, see, I found the volume of the base. I don't want the volume of the base. That's all wrong. I could have just changed the subscripts, but no. I felt like erasing everything. So 0.154 molar, 25 milliliters, 1.275 molar, and 2. H2SO4. So the base is on top this time because I'm trying to find the acid. Doesn't matter which side you solve for, the math looks the same. So 0.154 times 25 divided by 0.275 divided by 2 is, with 2 sig figs, 7.0 units. Well, the only unit I have left, milliliters. And that's really good because I was looking for a volume, wasn't I? There we go. You got 20H, got the 2 in the wrong spot. It's 7.0. You got 20H, you got the 2 in the wrong spot because you multiply it. That's 28 is 4 times 7. That's how I do that. Notice and there's a 2 in there. That would be my guess. Instead of dividing by 2, you multiply it by 2. Okay. That's it. That's all I got. It's not that much new math. We got that shortcut. First few problems on there, you're not going to be able to use a shortcut for because they ask you for the pieces along the way. Because not everything's a nice titration. Sometimes we do solutions that aren't just titrations. Okay. You got the 2 in the wrong place if you got 28. Yeah. Okay, do not try to do it in the space provided between the questions. You can use the back if you want to, a separate sheet of paper, I encourage, but do not attempt to do it here. Still getting 28? I think what you do is push times 2. Remember, it's on the bottom. You got to divide by both of them. Or you got to use parentheses. Yeah, order of operations, right? Oop.
In one of the homework assignments, I wasn't doing divide. I was doing divide.
Yeah, that doesn't work, does it? Yep. Wow, you mean we should have started the year with order of operations? That was our first assignment, order of operations. PEMDAS. I like order of operations because it makes a big order of observation of operations. Oop. Because that's the mistake people make. Oop. And it's shorter to write than PEMDAS or PEDMOS, depending on who you talk to.
That's true.
Is it PEDMOS or PEMDAS? Because I have put a few of the answers up on School Loop.